Awesome. Okay, cool. Let's get started because we have a lot of great stuff to go through. Just to introduce myself briefly, I'm Wehe, data scientist at Measurement Lab. We are a fiscally sponsored project of Code for Science and Society. Today we'll hear from Dave Chofnes of the Wehe team, which is just to appreciate all the work that they've done, but two, also to announce that the data from Wehe is now being parsed into our public BigQuery, which is thanks to a lot of work from members of both of our teams. So we'll just hear a bit about the journey that Wehe's taken to get where it is today, and also the data itself. And then at the end, I'll share a bit more about how one can access this data to use in research. Just a quick reminder, we have these calls every month. They're really just a way for us to get in touch with our community and hear from you all. So we welcome feedback and questions. And I'll also drop our community guidelines in the chat and just ask that we all respect those as we go along. If there's any questions, feel free to pop them in the chat. We'll do a Q&A after, but with that, I'll pass it off to Dave.
All right, thank you, Lai. So first of all, making sure people can see the slides. Great. So before I start a talk, especially when it's a topic that has potential political implications, I want to start by talking about the funding sources. Where is the money coming from? What influence might it have? So in the bottom right are the various entities that have funded this work at one point or another. When we talk about net neutrality, there's numerous stakeholders. There's content providers. Well, we've gotten some funding from Google and Amazon. There's telecom companies. Well, Verizon Labs has funded some of this work. There's regulators. The French national regulator ARCEP has partially funded this work. And there's the US National Science Foundation, which just has a vested interest in promoting science. So the important thing I want to convey here is that the funding has come from pretty much every stakeholder except the users themselves, the subscribers. And none of them have imposed any constraints in terms of what I can and can't talk about. That's just a little preface here. So today, what I'm going to focus on are measurements that we've taken over many years to understand what network providers are doing to change the kinds of service, the level of service that different applications get. And this, of course, is referred in general to a kind of net neutrality issue. The work I'm going to talk about is mainly based on an extensive analysis we did in 2019. This was joint work between folks at Northeastern University, including myself, and researchers at University of Massachusetts Amherst. That said, I will also at the end of the talk bring up some more recent results. Okay, so what's the context here? For a number of years, better part of a decade at this point, we've seen the rise of kinds of internet access plans that I'll refer to as gated in some way. And so here's an example. It's a little bit old, but the same kinds of things still exist. This is T-Mobile's advertisement for a service they provide. And you'll see they're not selling you internet, just plain internet. They're saying, now you can stream all the data you want for free, stream all the video you want for free. And with this service, they have some fine print, as always. And so if you make this fine print a little bit bigger, I want to focus on something that you'll typically see in these disclosures. So here it says detectable video typically streams at DVD quality 480p plus. And let's just pause a minute to think about what are they even saying here? Detectable video. Well, that word detectable is doing a lot of work in this sentence. And I'm going to come back to that later in this talk, what that actually means. And they're saying it typically streams at DVD quality, and they give you essentially a quality level, 480p plus. So what does that even mean, given that this is a network provider? This isn't the content provider who's telling you this is what you'll typically see. And so these kinds of things that exist for pretty much every single US cellular provider, in these disclosures, we're going to see that there's some gaps between what they're telling you and what is actually happening under the covers. And that's what I'm going to focus on today, and what are the implications. So why should you care about any of this? One thing to just note is there's a focus on video, and this makes perfect sense. Video is the dominant form of byte consumption in most networks today. So if you're streaming video, especially high-res video, it's going to take a huge amount of bandwidth. It's particularly challenging for networks because they tend to be coordinated, which means that if someone is watching something, they're going to watch it. A lot of people are going to watch it at the same time. So there's just a lot of demand at the same time as opposed to evenly spread over time. And when this happens, when demand exceeds capacity for a network, that can cause congestion, which in turn means that users are going to have a poor experience. Their video quality won't be as good, or there might be other issues. And so the thing that I want to highlight today is that while it may make sense that there are policies inside of networks that give different performance to video, the issue is that there's complexity hiding behind the simplicity in these disclosures. And one of the main things is that you have to ask yourself, if a network provider is saying that they're going to do something to video traffic, how do they even know that it's video? And I want to highlight this because for those of you on this call who might not be networking experts, I'm just going to give you one slide of my networking class. I teach Intro to Networking at Northeastern. And this is maybe the most technical thing you'll see in this talk. But what I tend to do when I'm talking, for instance, to regulators is I'll show them this and I'll ask them, what is this thing? And only a handful of people raise their hands. This is the IP packet format. So for those of you listening to this talk right now, you are getting data, you're getting the video and audio over small pieces of data put into these IP packets. And each one of these packets has information that tells you who it came from, where it's going, just like an envelope that you send in the mail. And just like an envelope you send in the mail, there's something inside, and that's the data portion. And so this data portion is where you're going to find things like video content, or if you're streaming audio, you're going to find the audio content there, or whatever else you're using on the internet. So all of that is going to go into the data portion. Generally speaking, the internet, the protocols, the standards, all the stuff in purple at the top of this diagram say nothing about the content. So that's one of the important things to notice here is that the way the internet was designed was not to specifically identify content, but to support anything that people might come up with. Now, in the traditional way that I'll talk about how networks forward data is that one of these packets comes through to a device called a router. And in general, they're only going to look at the destination. You're going to figure out where is this packet going so I can send it off and eventually get it to the destination. If it's this video feed right now, it's get it onto your computer. That's how most devices on the internet work. But what we found through our research is that there's other devices in the network that do something called deep packet inspection. So what I'm illustrating here is a device that's not a router, but it's a DPI, deep packet inspection middle box. And unlike a router, it does not look necessarily at the source or destination IP address, but it's going to look deeper into the packet. It's going to look at that data portion to try to figure out what is that network traffic and then do something accordingly. So what are these things doing? Through our research and research by others, we found a number of different things that network providers do with these DPI middle boxes. So one example is rate limiting. So an application may get limited bandwidth, much less than what's available. Another thing we've seen is that a box can transcode content. So it could take a high resolution image and turn it into a low resolution one. We've seen data caps. So if you've used too much data, then it may just either stop letting you access more content on the internet, or it might severely slow it down. And we've also seen zero rating, just like the example I showed at the beginning of the talk, where a network provider will mark certain packets as not counting against your data quota for your data plan. So it's called zero rating because they're charging you zero for the data corresponding to that network traffic into that application. Okay, so going back to the why should we care, as I told you, internet traffic does not declare itself as video or music streaming or telephony or Zoom or whatever. And so given that we have network providers that are trying to target specific applications, and the fact that the internet does not make it easy to tell what exactly is the application, that's not how it was designed, the implications of how these policies are actually implemented are very poorly understood. So we have a number of questions that we've been trying to address in our research, dating back to about 2014. Things like, what are these middle boxes doing? How do they work? Is what they're doing consistent with the public disclosures? After all, the people writing the disclosures are probably lawyers or generally not engineers, and the people who deployed the DPI boxes are different from them. There may be miscommunication there. We're also interested in what are some of the consequences, unintentional or intentional, of the way these policies are implemented. And then last, I'll talk about the measurements that we have that allow us to understand how are these policies deployed. So what are the practices taking place that give different performance to different applications, something we just call differentiation. Okay, so that's the background. Next, I'm going to talk about what are the challenges for actually understanding how to answer these questions and what's the approach we took. So I'll start with, in general, what are challenges for doing research on middle boxes and understanding what they do. The biggest challenge in general is what we generally refer to as ground truth. But how do you know what's actually happening? Ideally, you want to get your hands on the devices that do this kind of thing, and you want to figure out or know what is the network traffic that's going to be subject to their policies. Neither of these is straightforward. So when it comes to DPI devices, these typically are very expensive, tens, maybe hundreds of thousands of dollars. Believe it or not, they would not sell to someone like me, who has a pretty public profile of reverse engineering stuff like this and figuring out what they're doing. So I can't buy them directly, even if I have a large pile of cash to burn on it. If you look online, you'll find almost no documentation about what they do. And most network providers will never disclose what exactly is inside of their network. That's one challenge. Another challenge is, even if you know what is inside a network, these devices are designed to react only to certain traffic that crosses through them. And so that means that you can't just send arbitrary packets over a network and decide what happens. You have to figure out what are they looking for. You have to figure out what are their targets. And then you need to run some tests. And then once you've run those tests, you have to figure out, did the middle box do something to this traffic? How do you know for sure? So we address this in a few ways. One is that we were able to get our hands on a couple of real DPI middle boxes where we could log in and see exactly what they did to different network traffic. So this gave us clear signals for how they were classifying different network traffic as belonging to different applications. And it gave us control over certain policies that we could apply to those classes of network traffic. And then once we had this foothold, we could extend to do the analysis on unknown DPI middle boxes that were deployed in other operational networks. The other thing that we did is we focused on specific applications. So instead of sending arbitrary traffic, we decided the best way to tell if a DPI middle box is going to do something to certain network traffic for an application is to use the real network traffic that that application generated. Once we've done that, once we identify that something different is happening, then we can do further tests to figure out exactly what is it about this network traffic that is causing that behavior. And then what are the implications of that? So essentially getting down into the details of what are the DPI middle boxes actually doing and what could possibly go wrong. Okay, so before I dive into some of the things that we found, I just want to give you a very high level overview of our method, and we just call it record and replay. The idea is that you have some application of interest that you want to test for differentiation. Let's say it's Netflix. The Netflix, of course, has an app that you can run on a mobile device. And they also have their servers located all over the internet. And if you want to figure out what is the network traffic that Netflix generates when you stream a TV show or a movie, you just go ahead and initiate a stream over a network of interest, say a cell network or some other network where maybe you know that there's no differentiation. And then, or another way that you can ensure that there's no differentiation is that you could take that network traffic and you can actually send it through a tunnel, an encrypted tunnel, to some proxy server, which is where you can also do something like record the network traffic. The idea here is establish an environment where you can reasonably believe that there's going to be no interference with the network traffic, and it's the real applications traffic. So we've recorded this now. We know what the client sends. We know what the server sends in response. And now we can use this to run tests. And the way that we're going to do this is now users of our software, they install an app on their mobile device, and that mobile device is going to communicate with our servers. It's no longer Netflix's servers or YouTube's or whoever else's. And so the idea here is that we send that exact same traffic. So it's Netflix's traffic, but it's between our app and our servers. So we have complete control over everything here. I should amend that. The only thing we don't have control over is the cell network itself, or the test, or whatever network we are trying to test. So we're going to send this same network traffic that Netflix generated, first with no modification, and then we're going to do something that essentially hides the fact that it's Netflix. And so you could do this with a VPN tunnel. In practice today, we've modified this to be something a little bit different that doesn't require a VPN, but has the same effect. Now, what happens when you run these two tests? If you zoom in on a network of interest that has a DPI middle box, what's going to happen is the traffic that we didn't change or hide in any way is going to go through that middle box, and it's going to be able to do whatever it does to classify that traffic. And when we send traffic through a tunnel or otherwise obfuscate the patterns, the middle box is essentially not going to be able to see any of those things in packet contents that could have told it that this was Netflix. So we run pairs of tests. One we call exposed, where we don't change anything, and the other we call control, where we essentially make the traffic look like nothing. On our servers, we record all kinds of data about what kind of performance we saw for these flows of data between our apps and our servers. And then we conduct an analysis to answer the question, did we see substantial differences in performance between exposed and controlled? And was it beyond sort of random chance? After all, if you're on a wireless network, there's all kinds of things that can cause interference and differences in performance. And we want to more confidently conclude that what we're seeing is actually some policy that is changing performance implemented by the network and not just something else happening. Okay, so that's our high-level approach. And now I'll tell you a bit about what we learned using this approach. So high level, you may have a lot of guesses as to what these DPI devices might be looking at to decide something is video or whatever application it is. We thought they might be looking at IP addresses. We saw no evidence of that. They did not care what the destination was, and that makes a certain amount of sense because there are servers that will serve video and other content that is not video, and so that's not a great way to target video. We also saw that they weren't looking at things like the timing between packets being sent and a number of other factors that we hypothesized might be at play, but in fact weren't. So what were the DPI devices looking for? We found that they're looking for specific keywords or bytes, generally in the payload portion, the data portion of packets. That the way that they're doing it is extremely simple, to the extent that the devices don't generally have an understanding of the protocols that they're analyzing. They're just looking for certain patterns. And that's going to have implications. So just to give you some examples here, I'm showing a simplified IP packet where it's an HTTP GET request. And everything that I've shown in black text here refers to something that a DPI device could look at in an HTTP GET request to infer that something is either specifically Netflix or more generally video. You see there's a lot of different places, a URI, user agent field, host parameter, and content type. So this, in fact, is what we saw in our testbed. We saw, for instance, the text NBC Sports, all one word, was being used as a matching parameter for NBC Sports video in the URI field. For host, we saw .Spotify being used to identify Spotify traffic interestingly, including the leading and trailing dots in the host. For user agent, you see Pandora, content type, click time. All this seems pretty straightforward. And at this point, you might be thinking to yourself, well, that doesn't seem so bad. It seems like they know what they're doing, right? They're getting it right. Well, I'm going to give you another example. Here's a user agent string, Galaxy Wars multiplayer. For those who don't know, and I was with you, it is a game that people play on their mobile devices. It's just an app. And we sent this through our test bed, and we found that this was classified as iPlayer. So what is iPlayer? iPlayer is BBC's video streaming service. So here's an example where gaming traffic was being classified incorrectly as video. And why was this happening? Well, I just highlighted in bold text, Galaxy Wars multiplayer has the text iPlayer embedded inside of it. And so this is one of the issues with the way that DPI detection works. They're not looking for text that is necessarily going to give you 100% accuracy. And as a result, not only may they miss certain traffic that belongs to a class, they also might misclassify stuff that has no business being treated differently in their network. And at this point, I'm sure many of you on the call are thinking, Dave, you just gave me an example of plain text traffic. Everything uses end-to-end encryption these days, uses TLS. And as a result, all those payloads that I just showed you should not be visible to the middle box. They'll just be essentially gibberish, which is what I'm trying to illustrate here. And that is true. Pretty much all traffic we see today that is of interest for differentiation is end-to-end encrypted. And so you might think to yourself, well, I guess that's it. We don't have DPI devices able to do anything anymore. We shouldn't have any concerns. Well, that is simply not true. It's the case that DPI can't see hosts, user agent, all of these things that is encrypted in a TLS connection. However, the vast majority of TLS clients today use a configuration where information while the connection is being set up is sent in plain text, meaning that middle boxes can see when you establish a connection that you are trying to reach, say, googlevideo.com. And if that isn't enough, they can also look at the certificate that comes back from the server, and they can see things like common names that may indicate this is Google, or subject alternate names. And so between the SNI field not being encrypted by default and this client hello and server hello not being encrypted, it's actually a good amount of data that DPI devices can use to infer what the content is, and then label something and treat it differently. So what are the issues with this? One thing is that for a device that relies on googlevideo.com as a way to classify video traffic, the simple fact is that some of those connections may not be video. There is non-video being served from googlevideo.com. And if Google chose, they could serve videos from just plain google.com, in which case they would not get differentiated by networks that use DPI in this way. So you could have misclassification going on both ways. And because of encryption, there's no way for DPI to distinguish what is inside of those packets and separate out the video traffic from the non-video traffic. Okay, so I just want to give you a recap of what we've talked about so far, and then I'll move on to some larger scale analysis that we did. So how do we approach this problem? Like basically which applications are affected and how do these devices work? The answer is we don't know which applications are affected, so we're going to record and replay real traffic from real apps and then include that in our app for testing against deployed networks. How do we know, once we've done a series of tests, that with any confidence that there's been differential treatment for one kind of test versus another? Because this is not meant to be a technical talk, I'm not getting into these details, but we came up with a modified version of a statistical test that gives us very high confidence. And we've also used other statistics to then use collections of tests run by multiple users or subscribers of the same ISP, and use that to identify what are the rates at which different content is being limited. In that case, we're talking about download rates. And we've done all of this with a little bit of ground truth that came from buying and acquiring DPI devices and identifying that they're using what we call matching rules. They're not even as sophisticated as regular expressions, but they're really just looking for certain bytes or certain data at certain locations and looking for a match. Okay, so next part of the talk, I'm going to focus on what we learned beyond our lab environment. So we set about in around 2015 to take what we had done in the lab and make it much more broadly available. So the public could help us run these tests and we could get much more insight as to what is happening on the internet. We picked some popular apps at the time and some that were not as popular. We picked some that use TLS, some that don't. And we even picked a UDP application in Skype. And we have video and audio and teleconferencing. So we have a number of different types of applications. Again, this is 2015. We have updated applications I'll talk about later. But our approach was to build an app allowing other people around the world to run tests. And so we released this in November of 2015. It was out, mostly unchanged for about 2 years. And so in those, important 2 years, this is, when we had some net neutrality regulations that were passed by the FCC, and of course the change in administration, you might wonder, what did we find? The answer was pretty much nothing. Nobody was using our app. Nobody wanted to download it. And so we realized we had to go back to the drawing board. We had some problems. One, though Android is lovely, our tool only worked on Android. So that's a large fraction of people who were not able to run tests. It required using a VPN, which if you can ever avoid in designing anything is something to avoid, as we learned the hard way. People didn't really understand what we were even doing, so they didn't have incentive to use the test, and it had a terrible name. It was called Differentiation Detector, which, as you can tell, I'm already stumbling over. So we had a new approach. So we went back to the drawing board. We then produced both an iOS and Android app. We removed the VPN dependency. So instead of sending traffic through tunnels, we use not randomized, but bit inverted payloads for reasons I won't get into in this talk. We came up with, I'll say is a better name, at least as an easier name to say, Wehe. And then we submitted this for approval in late 2017, approval to the App Store. So for the Google Play Store, we already had an existing app. We were just changing the name and there was an overhaul in code, but it was approved nearly immediately. For iOS, it was a new app. So it had to go through a presumably rigorous review. And what happened? What happened is that Apple said, no, they rejected our app. I appealed it. On appeal, they said no. There was another, I think, final appeal, and they still said no. As you can imagine, now, by the way, it's January 2018. I was pretty incensed by this and also just confused as to how we got there. And so I decided to memorialize what had happened in a tweet back when it was still Twitter. And so, for example, among other things, they just told me that they did not think the app was appropriate. This is a time when there was a lot of public debate about what new net neutrality regulations should be under the Ajit Pai FCC. Well, ends up that my little tweet storm got the attention of some people. And so Motherboard was the first to write a story about this, that Apple was, for reasons poorly understood, blocking an app that detects net neutrality violations. This then became the top story on Reddit, which then led to an enormous surge of activity. And so this graph is showing the number of tests we have over Wi-Fi and cellular over time. And this is the first couple of years of the new versions of the apps. There's a log scale on the y-axis here, and to be honest, it doesn't even capture the true extent of what we were doing or the amount of interest in the app. For one, I just told you Apple had rejected the app, so how is anyone using it? These are all just Android tests. So we only had Android users using it at once, and they completely overloaded our servers. This is before we were on MLab. And so we had well over 100,000 test attempts within that one day that story got released, and we've had tens of thousands of tests coming in per day for a while after that. Where we are today, we've had 2.4 million tests run over Wehe by our users, currently growing at about 100 per day, but I think given that net neutrality is back in the news, we're going to see that jump up again soon. In terms of where our tests are, we have a huge bias towards the US. That's why you see it in a darker shade, as you can imagine. First of all, the app was originally only available in English. It is now also available in France, which is why you see that one of the next biggest regions is France, where RCEP encourages French residents to use the app to detect whether there's net neutrality violations and violation of their rules and laws. So we got a lot of test data. So in a certain sense, though I was not happy that Apple rejected our app, I should thank them for all the attention they gave us. Just to kind of circle back on that, yes, they did eventually approve the app. It involved some executive calling me who just happened to have a Northeastern degree to make that connection to where I'm a professor. And they decided they would take a second look. And I just had to send all the same stuff back to them again. And within 24 hours, it was on the store, the Apple App Store. And so now today, and for many years now, people have been able to download it on both platforms, iOS and Android. Okay, so a little bit of a journey, but we got there. And now the question is, we have all these tests. What did we find? I'm going to preface this with two things. First of all, I'm going to start with just cellular findings because that's where the action tends to be. I'm going to talk about other findings on the next slide, but this is all cellular. And then the other thing is everything that I'm talking about on this slide is based on our extensive analysis in 2019. It ends up that analysis was a little bit painful to do before our data got loaded into BigQuery. Now it's in BigQuery. That's part of why I'm giving this talk today. And so the things that were very painful and took hours or days or months of time can now take minutes. This is what we found in 2019. Most of what I'm telling you about is present today. So first I'll focus on the US because the US is where we had rule changes in 2018 that made it so that giving different performance to different applications is okay, or allowable, I should say. So what did we find? Each line, I want to point out, is a collection of network providers that limit video to the same rate. So for instance, that first line, C-Spire limits video traffic to 1 megabit per second, whereas the second line, Cricket and TFW limit it to 1.2 megabits per second. The other thing that you'll notice here is a little bit subtle is that some of the network providers' names are in italic. If that's the case, then that network provider is on multiple lines in this table. And that means that they have some subscribers throttled at one rate and other subscribers limited to a different rate for their video. So that's one of the big takeaways I want to focus on here already. So first of all, nearly every US cellular provider is rate limiting video traffic, at least some of it. And there's a wide range of different rates that they use for limiting that traffic. And sometimes even for the same provider, different subscribers will get different rate limits depending on what their plan is. And there's no way for anyone to know this, or for content providers to know this in advance. Now, I've been focusing on the US because that's where most of the action is. It is not the only place. We found evidence of rate limiting in Canada, Germany, Israel, Bahrain, and Brazil. We've also found it reasonably pervasive in the UK. And though Wehe is not designed to detect censorship, the simple fact is that when content is censored or blocked, it is throttling to a rate of 0 bits per second. And so some of our users in the United Arab Emirates have used our tool and identified that Skype is blocked there. Okay, so these are the cellular findings. I'll move on to Wi-Fi. So when someone does a test on Wi-Fi, what happens is they're actually going through whatever network connection their access point is connected to. So just again, the context here, you're on a cell phone, you may have a connection via your cell network or your Wi-Fi network. And so we can tell, and we know that in the test, what's being used. And if you're on Wi-Fi, what we tend to find is that it's very rare that we see any kind of application-specific treatment. We don't see differentiation very often at all. So you'll notice Comcast isn't here. Comcast, which famously blocked and throttled BitTorrent traffic in the earlier days, before streaming was a big thing. They are not doing anything like this. What we do see is differentiation on networks that, if you look at what they are actually wireless, limited spectrum networks. So for example, Viasat uses geosynchronous satellites to provide internet access. And that's a very scarce resource, a scarce bandwidth on those networks. And so just like cell networks, they are implementing these kinds of policies. We've also seen long-range wireless networks that are the backhaul here. So it's not a fixed line connection. So the vast majority of cases that we see when a user is doing a test over Wi-Fi and we see that there's differentiation, it's usually because there's some kind of wireless network behind it that is cellular, long-range wireless, or satellite. And so the truly fixed line access is where we tend not to see this behavior. One other thing I'll highlight, so this is just another view of the same kind of data, where each line is a provider, and then there's information about which apps we've detected were being rate limited, what were the rates they were using, and how many tests we had for them. And I want to focus on the middle column here. And so I've just put the logos of the different video providers to let you know who is being, where we have the evidence of these different applications being throttled. And you'll see it's not the same in every column, every row. And so that's another potential issue here. After all, video doesn't declare itself as so on the internet. That has to be inferred, which means the DPI devices have to be programmed to look for specific things. And as a result, there's an opportunity to not cover everything. There's literally no way to program a DPI device to detect every single kind of video. And that's why at the start of this talk, you heard me talk about the heavy lift of detectable video. Because in the end, there's always going to be new video providers. They're always going to potentially change what domains or other text might be available to DPI devices. And so there's no way for these devices to be perfect. Okay, so a few other takeaways, just kind of popping up a level in terms of things that are relevant to policy here. I just pointed out, not all video apps are rate limited. What does this mean? It means that there's an unlevel playing field where network providers are essentially picking winners and losers. Pretty much everyone, if they're going to rate limit, they're going to rate limit YouTube. That makes sense. That tends to be the biggest contributor of bandwidth consumption in any given network. We see large players like Netflix and Amazon are often limited. We see that smaller players like NBC Sports and Vimeo are almost either rarely or almost never throttled. Another question we had is, are they doing this to video because it's overloading the network? And if so, wouldn't it make sense that they would do it only in response to load? So I actually went out and I happened to know someone who was an engineer for a very large USL provider. And I said, hey, are your networks overloaded everywhere all the time? And the answer was, well, no, of course not. That's ridiculous. Like it wouldn't work. We'd have terrible service. There are hotspots and it's at certain places and certain times. I said, okay, that's interesting, because when we see the way that the policies are implemented, when we detect differentiation in Wehe, we see it 24/7. We see it all the time, and we see it everywhere in a nationwide network. We don't see it as something that's happening in response to load. And so this begs the question, is this approach even reasonable network management, which is a standard that network providers are often held to in regulations? The next thing I want to, adjustment here. The next thing I want to point out, and I've already mentioned before, is that the rates to which video content is limited varies not only across carriers, but even within a single carrier. Well, that means if you're a content provider trying to provide good video quality to your subscribers, you have an increased burden. You have to make it work at 1 megabit per second, and then 1.2 megabit per second, and then 2 and 2.5 and 4. That's something that maybe a well-staffed team at an existing, an incumbent content provider like YouTube or Netflix or Amazon they can handle that. They have a great, very large engineering team and lots of cash to spend on that. But if you're a new entrant to the market, this is potentially going to limit your ability to compete with others, with the incumbents that are there, which is another issue that comes into play when we think about the unlevel playing field this creates. The other thing I'll mention is that these approaches, in many cases, cause a lot of the data that's sent by content providers to be dropped, meaning it never is received and that it has to be retransmitted by the content provider. And even though the cost of sending a byte of data is not very much, at large scale, having to retransmit that data does actually cost money. This is another potential harm. And not every instance where we've seen the kind of differentiation we've detected leads to high loss, but a lot of them do. And this is something that could be addressed much better through other mechanisms. The last thing I'll mention is the relation to recent discussions on the digital divide. So the lockdown period of COVID taught us in a very hard way that a large portion of people in the US and abroad have limited or no access to the internet at home. So we've all read the stories about people trying to do their homework or attend classes via McDonald's Wi-Fi. For many, the only internet access they have is a cellular connection. And so now I've just told you that every cell provider in the US is going to be rate limiting video. That's going to limit the quality of the video that they can receive. And now, as we continue to have a lot of our education online and had all of it online during the lockdown period, we have to ask the question, what impact is this having on those who are in the sort of underserved category? Are they going to have a different educational experience and fewer opportunities because of these policies? Okay, so I'm going to wrap up my talk by just mentioning a few things. First of all, Wehe has been running continuously in its current form since 2018. If you go to our website, you can see some summaries of the data we've collected. One of the things is that it's hard for us to break it down by time period, or at least it has been hard until recently. The good news is that our data, which has always been publicly available, is now automatically loaded into BigQuery. Why is that important? Because in BigQuery, now you can ask questions of the data without having to run your own major server infrastructure like we do at Northeastern. And you can run these analyses within seconds or minutes at worst. So anyone can do this.
And Dave, sorry to interrupt your flow, but if you want to just
yeah.
look the last slide, I can just speak to that briefly. Just so we don't repeat ourselves. I think it's the last one after your question slide. Yeah, great. Okay. So I thought I would just bring attention to this. I'll also put these slides in the chat, but basically there's a link there to the BigQuery sign up. So actually, if you're here, you might already get the discuss@measurementlab.net emails. That means you have access to the data as well. But if not, there's a link there. It's really easy. You just sign up for our mailing list essentially, and that gets you access to all of the data, not just Wehe data. And then all of the newly uploading data is going to be in the Wehe raw table, and the link there has the schema documentation and then some sample queries as well to show how to look into it. So as Dave was saying, hopefully now this makes analysis of this data a bit easier. And these links are in the last slide of the slides.
Okay, thank you, Lai. So the last thing I want to talk about before I conclude is just what have we seen, and even just the past few months since data started getting auto-loaded into BigQuery, just focusing on the major US carriers. Who are they throttling? You'll see some common names. I've ordered them in an intentional way. You'll see Hulu, Amazon, Disney+, YouTube, and Netflix. Those are all covered by all of the major cellular providers. But you'll see then there's some differences. So AT&T will throttle Facebook video, but we haven't seen evidence of them doing it to Twitch or Vimeo or NBC Sports. Whereas T-Mobile will do this to Twitch, Vimeo, and NBC Sports, but not Facebook. And last, Verizon will do Twitch and NBC Sports, but not Facebook video or Vimeo. And then again, we see that we have subscribers that sometimes are rate limited to 1.5 megabits per second, sometimes 2 megabits per second. These typically correspond to different rate plans that subscribers have signed up for. T-Mobile, generally around 2.5 megabits per second, though we've seen evidence of some other bit rates as well, or sorry, rate limits as well. And Verizon, we still see the 2 and 4 megabit per second categories. This was through a relatively simple query that we were able to execute within a very short amount of time on BigQuery. And so we're also going to be working on uploading all of the historical Wehe data into BigQuery. So then you could really pick and choose any window and understand how this has evolved over time. Not there yet, but in the works. So if you want to know more about the project, we have our website, wehe.metal.mobi. We have research papers if you want to dig into those details. We have code and data if that's more of your thing. Also links to the iOS and Android apps, which you can also find just directly in the corresponding stores. As I already mentioned, there's the data in BigQuery you can access that I hopefully told you about where to get access to. I've also made some public remarks both to the Massachusetts State Legislature when they were considering net neutrality legislation, and also through public comments to the FCC. And then last, I just want to thank all the people who have made this happen, from the students working on the project, our sponsors, everyone at MLab, without whom Wehe honestly wouldn't be running today. And of course, the users of our software who run the tests that allow us to see everything I talked about today. So that's it. And at this point, I'm happy to take any questions. I see there's some, I'm opening up the chat to see. All right, so first question, will I create software for Windows and allow testing on cable and satellite networks? So the short answer is unfortunately probably not. I don't have someone who on my team who knows how to do that development, and we also have always had an extremely small budget. So we open source the code with the hope that people who might want to contribute for different platforms would be able to do so. That said, it's been out there for over 5 years and no one has done so. The best we can say is that, if you are testing your home network and it's on cable or satellite, you can always download the app on a mobile device, assuming you have one, and you could run the test over Wi-Fi, and that will tell you what's happening on those networks. But unfortunately, we do not have a native way for you to do testing on Windows. The only other option that I'll mention is we have a command line client, but that's not usually what most people want to use. So if you're familiar with the command line, you can actually you can download that, or basically clone our repository, and you can run tests and get the same results you get from the app, but it's all going to be in text. So it's unfortunately not very user-friendly. So I have another question here. Do the methods used by middle boxes to identify streaming data change over time? If yes, how do you keep up with the changes? The short answer to the question is yes. They do change over time. This, as just one very blindingly obvious example, Amazon video traffic used to not use TLS. So the content had DRM on it, but the individual requests were still over plain text. And so when they eventually changed to TLS connections, the DPI devices couldn't rely on stuff they were relying on inside the HTTP request. Then they had to do their TLS-based approach. And so the way that we keep up with it is that we have to do new recordings, and recordings of network traffic, we have to put those in the app, apps, plural, Google and Android and iOS, and then we have to push those to the stores. Users have to update those. We have to do the same thing on the server side. It's unfortunately a little bit painful to do that, but it's something that we do from time to time. And as part of a recently funded NSF project, we are looking at ways to make this easier to adapt. So that's actually something we've very recently, as in like the project technically started October 1st, so 4 days ago, that we're looking we're looking into, because that's always been a big pain point for us. Okay, so I have another question. How do you think middle boxes would react to fully encrypted protocols such as ZCH, which is encrypted client hello? Would we see more IP-based classification? This is an excellent question. I have no idea what's going to happen. I think if ECH or even ESNI is deployed, encrypted SNI, the DPI devices will have trouble. I don't think IP-based classification is going to work. There's just too many content providers who rely on having infrastructure that is shared with others. And so anything based on IP is very likely to get it wrong, even worse than what I just talked about today. Assuming that the content provider is not also the network provider. If the network, of course, there's consolidation in this market. So, if you're Comcast and it's Peacock, you know what all the IPs are, and you could do whatever you want. But when it comes to the other cases, the more general case, I don't think IP-based classification is going to work well. The only thing that I could also add to this is content providers and network providers don't operate in a vacuum from each other. Though this is not something I can point to any documentation for, let's just say that I've gotten the impression that the network providers and content providers do talk to each other. And as part of those conversations, they may decide to do or not do certain things according to, say, what a network provider might need. So we've had ECH as a standard available for several years now, and it's only just barely being turned on. Cloudflare has it on by default now, I believe. And actually, I'm not even sure if it's by default. But it's telling that there have been strategies to avoid the DPI devices and their rate limiting, but they have not been they've not been turned on in many cases by content providers. So I'll leave that out there. All right, I think Ethan just has a clarification. So another question is whether a certain device or certain server functions as a middle box. To be honest, we've never really known what devices are in any network. And so as a result, I generally can't tell you what device serves what purpose, unless it's like one of the two that I have in my lab. And even those are pretty old at this point. So there was a time when I could tell that it seemed like the same classification rules that we saw in our lab were being used in operational networks. But that is not something that I can really speak about in general. Okay, so another question here. Zero rating is beneficial to both the network provider and content provider, so it could easily involve contractual arrangements and manage topology or address assignments. Have you detected any such arrangements? So that's a great question, and that speaks to the limits of what Wehe can do. So Wehe can only tell if different network traffic is getting different performance based only on the contents of the traffic. So if the way that zero rating is done, for example, is based on contents of traffic, then we'll see that there's differentiation, but we don't know if it's zero rated. That's not something that we can tell just by looking at the network traffic. Similarly, if it's a topology or IP address specific thing, again, we won't see it because the IP addresses and the topology are related to the servers we control, which today is MLab in like one AWS instance or EC2 instance on Amazon. And so the bottom line is that we actually can't answer that question. There are other types of tests that one might think about to try to look for that, and it's definitely feasible, but it's not the ones that we've implemented. The ones that we implemented were not done arbitrarily. We chose to design Wehe in this way because of what we found being done in the wild. And so we tailored our tests to the practices of the day. We see those practices are still in place. But if there's new ways, think of, if ECH is deployed, if there's new ways that differentiation is happening, then we'll need to modify our tests to be able to detect it. And there might be some things we can't very easily detect. Interesting fact, there was a time when, so it ends up that some AT&T subscribers who found Wehe and ran tests saw that their network traffic was being rate limited. There was a feature called Stream Saver that AT&T had implemented and deployed at that time and was turned on by default. And so a lot of those subscribers started calling to complain to AT&T. And when that happens, that actually costs the network provider money because they have to pay people to answer those phone calls, and that gets noticed. And so through discussions with AT&T, I learned they wanted us to show something to our users as to what was going on. And of course, I only wanted to do this in a way that everyone, not just AT&T, but every network provider could give us a message that we could display to our users. And that would require something like an API where I could ask the network, what is the configuration for the subscriber? And then I could show it to that subscriber. So I could show them accurate information about why they were seeing what they saw. That conversation ended, and we did nothing to Wehe because that was not something that the network provider had. So all these questions about zero rating, about what are even the different rate plans and the policies applied to them, these are generally things that as researchers we have no insight into, and often network providers are at least not able to provide much information even to consumers about. All right.
I will flag that,
other
yeah,
questions?
we're getting towards the end, and you've done a heroic feat by that presentation and all those questions. Thank you everyone for joining. If you have follow-up questions, feel free to reach out. Dave, I'm not sure you provided your contact, but to the discuss list would work as well. And thanks for joining. We have these every month, and feel free to follow up with any questions. Thanks, everyone.
Thank you, everyone.